Welcome to our discussion of chemical kinetics, which is Module 6 in your preparation for the CLEP chemistry exam. Okay, so let me tell you a little bit about exactly what we mean by the term chemical kinetic. Chemical kinetics has to do with the rate of a chemical reaction, which basically means how fast something is taking place or how quickly the chemical reaction is taking place. Okay, and so we care about how fast it's taking place. Just from the practical point of view, you know how long to wait for your reaction before it's done, right? You want to know if your reaction will take 1 minute or 1 second or 5 hours or years. Okay, you want to know like how quickly this is happening. So that's one important thing. The other important thing, as far as kinetics goes, is you can use it to understand the mechanism of a reaction, meaning how exactly is this reaction taking place at a molecular level, right? Which bonds are breaking, which bonds are forming, how are things combining and rearranging, and how are these things colliding and moving around and doing all the wonderful things that chemicals do, right? How is it all happening? Okay, just as a side note, if you ever have to do these experiments, these measurements are really hard to get accurate and precise numbers for because everything is changing with respect to time. Okay, and so kinetic experiments typically take a long time to carry out. So let me tell you a little bit about some of the different factors that might affect the rate of a chemical reaction. Okay, what's going to influence exactly how this reaction is taking place? Well, it'll depend a little bit on the type of reaction that you have and what's involved, but very loosely speaking, there are probably 4 things or so that can pretty severely impact the rate of a reaction. Okay, first is concentration. Okay, concentration means the amounts of the reactants that are present, and the reason that matters is because we're thinking of chemical reactions in terms of collisions, right? Things are bumping into each other and doing things. So the higher the concentrations are, the more likely they are to come into contact with each other and collide. And so the more they can collide, maybe the faster the reaction will take place. Okay, and so generally speaking, not always, but generally, as they increase the concentrations of the reactants, the rates of the reactions also go up. Okay, another thing that might matter is pressure, although this really only affects gases. Okay, liquids and solids are pretty incompressible, so their properties are not really changing too much when the pressure changes, but gases are pretty highly compressible. So when I change the pressure, I can also change things like volume, right? If I increase the pressure and kind of squish everything together, volume is getting smaller. Now they're also more likely to collide because there's a much smaller area or volume in space for them to get together. Okay, so generally speaking, higher pressures also make the reactions go a little bit faster. Next thing that might affect reactions is temperature. Okay, temperature always affects reactions, or virtually always affects reactions, because temperature is related to the average kinetic energy of the molecules, right? So the greater the average kinetic energy, the more likely they are to move around, and then the more likely they are to collide with each other and do something. Okay, the last thing that can matter is if I have a catalyst around. Okay, we'll talk a little bit about catalysts later. Catalysts could be really, really small things like protons or water molecules, or they might be enormous molecules like proteins that basically speed up or occasionally slow down, but usually speed up a chemical reaction, usually by changing the pathway, right, how the reaction happens. Think of it as a shortcut for the reaction to take place. This is what's meant by the mechanism, right? They change the mechanism of the reaction. And so if we understand how a reaction depends on all these factors, we can optimize it to get as much product as possible in the shortest amount of time possible. Okay, so what I'm going to do now is give you a little bit more of a mathematical description of chemical kinetics and rates of reaction. Okay, so let me show you how you can measure rates of reactions. Let's say that you have some kind of chemical reaction with reactants R that are going to form products P. Okay, I can think about this reaction in 2 ways. I can think about it in terms of how quickly the reactants are being used up, consumed, decreasing, or I can think about it in terms of how quickly the products are increasing and going up. Okay, and so I can monitor either changes in the reactants, or I can monitor changes in the products, or if I really want to, I could even measure changes in both. Okay, and so let me show you what this looks like graphically. Here are 2 different pictures showing you concentrations of reactants and concentrations of products, two different graphs, and they both have time in them as my x-axis. Okay, and so on the left side, you can see what happens to the reactants. Okay, initially, they start out at a certain level, which we'll call R0, and then over the course of time, the amount of the reactant decreases. And it decreases at a certain rate. And eventually, it stays constant. Okay, when it doesn't change anymore and stays relatively constant, that's when I've reached equilibrium or steady state. Same kind of thing happens for the products. Okay, let's assume that when I start, there are no products, so the concentration of the products is 0, but then over the course of time, the amounts of product steadily goes up and up and up, and eventually it kind of saturates and stops increasing. And then when that happens, at this point in time, that's also when I've reached equilibrium. Okay, so I can think about the rate of the reaction as being related to the slopes of these parts of the graph. And when I use the word slope, I kind of think of lines. Okay, and so I can think of the slope of the line, right? The change in the y value divided by the change in the x value. Okay, or if you've taken a little bit more math, this is also something called a derivative, right? The first derivative of the function. Change in y over change in x. Okay, and so I can think of the rate of the reaction as either the derivative or the change in the product's concentrations over time, or the derivative or the change in the concentrations of the reactants over time. So because the reactants are decreasing, I need a minus sign in front, right? So minus dr dt, or minus the change in r over the change in time. But for the products are always increasing, so that already is positive. That has a positive sign. So that's going to be plus dp dt, or the change in product concentration over the change in time. This means that the rate is really the slope of the tangent line to the curve. Okay. Problem with this is it doesn't take into account stoichiometry of the reaction. Okay, so maybe I have something like R goes to 2p. Okay, so in this case, for every one molecule of R that I use, I form 2 product molecules P. So in that sense, the rate of formation of product is twice the rate of loss of the reactant. And so to take into account the fact that I might have different stoichiometries, I have to use these coefficients. Okay, if I want the rates to be the same, I can take the amounts of the products and divide it by 2. Okay, and so I would say that the rate of product formation is twice the rate of reactant formation, or if I want to make it like 1/2 of the 2, that's equal to the rate that I began with. Okay, and so what I can do is write down an expression for the rate is equal to 1 over the stoichiometric coefficient, nu sub I, times di dt. Okay, and so basically, in the case of R goes to 2p, if I think about it from the point of view of the reactant, this would be minus the change in the reactant over the change in time, or 1/2 the change in the concentration of the product over the change in time. And again, I use this 1/2 because I know that the product is being created in this particular case twice as fast as the reactants are. So I want to make them the same number.